What if you could generate video that actually responds to your actions? Not just predicting what comes next, but truly simulating a world you can interact with in real time. This is the promise of world models, AI systems that go beyond passive video generation to become interactive simulators. They understand physics, respect object permanence, and respond to user input like a video game would. Today, we're diving into LingBot-World, an open-source world model from the Robbyant team that's pushing the boundaries of what's possible. It can generate video at 16 frames per second with long-term memory and full action controllability using WASD-style keyboard controls. What makes this particularly exciting is that it's completely open source. The code, the model weights, and the inference pipeline are all publicly available. This is a significant step forward for the research community, as most high-capability world models have remained closed or proprietary. In this video, we'll break down how LingBot-World works, from its data engine to its three-stage training pipeline, and explore why this represents a major advancement in open-source AI capabilities.
To understand why LingBot-World matters, we need to distinguish between two fundamentally different approaches to video generation: dreamers and simulators. Current text-to-video models are essentially dreamers. They can generate visually impressive footage, but they lack true understanding of the world. Objects morph unexpectedly, physics gets violated, and there's no concept of object permanence. You can't interact with them because they're not simulating reality, they're hallucinating it. Simulators, on the other hand, maintain consistent world states. Objects persist even when the camera looks away. Physics behaves predictably. And critically, user actions lead to logical consequences in the generated world. Looking at the comparison table, we can see that LingBot-World addresses four key challenges. First is high dynamic degree, the ability to generate scenes with complex motion and interactions. Second is long horizon generation, maintaining coherence across extended video sequences. Third is real-time performance, generating frames fast enough for interactive use. And fourth is the open-source requirement. While other models might achieve one or two of these goals, LingBot-World is currently the only fully open-source model that tackles all four simultaneously. This positions it as a unique contribution to the research community.
The foundation of any good world model is high-quality training data. LingBot-World's data engine is built on three pillars: data acquisition, data profiling, and data captioning. For data acquisition, the team collects from multiple sources. They gather real-world videos with natural camera motion patterns, they extract game footage that comes with built-in action signals, and they generate synthetic data using Unreal Engine, which provides perfect ground truth for camera poses and scene geometry. The data profiling stage is where quality control happens. Not every video is suitable for training a world model. The pipeline filters based on resolution, duration, and motion characteristics. Videos that are too static, too noisy, or too short get filtered out. Finally, the captioning stage creates the semantic descriptions that will guide the model during training. But this isn't just simple captioning, it's hierarchical. The system generates three types of descriptions for each video, which we'll explore in more detail. This three-pillar approach ensures that the model trains on diverse, high-quality data with rich semantic annotations. It's the kind of careful data engineering that often separates successful models from failed experiments.
Let's zoom in to the data profiling pipeline to understand how raw videos become training-ready assets. The process starts with basic filtering. Videos are checked for minimum resolution, at least 720p, and appropriate duration. Transnet V2 then segments longer videos into coherent scene clips. Next comes semantic analysis using a vision language model. This extracts quality scores, motion magnitude, and scene type classifications. Videos with artifacts, watermarks, or inappropriate content get filtered out at this stage. The geometric annotation step is particularly clever. Using MegaSAM, the system estimates camera poses throughout each video. This gives the model crucial structural priors that help it understand spatial relationships in the scene. Finally, the hierarchical captioning creates three distinct types of descriptions. Narrative captions describe the overall story, camera trajectory, and how the environment evolves. Scene static captions focus purely on the environment without any characters or motion. And temporal captions provide time-aligned descriptions of specific events at each timestamp. This multi-granularity captioning allows the model to decouple semantic control from motion dynamics. You can describe what should happen separately from how it should look, giving much finer control during generation.
LingBot-World uses a three-stage training strategy that progressively transforms a general video generator into a real-time interactive world simulator. Stage 1 is pre-training. The model starts from 2.2, a 14 billion parameter video foundation model. This provides the baseline capability for high-fidelity, open-domain video generation. The model already understands textures, lighting, and general visual coherence. Stage 2 is middle training. This is where the model learns to be a world simulator rather than just a video generator. Action conditioning is introduced. The model learns to respond to WASD-style control inputs. Long-term consistency is trained, teaching the model to maintain coherent world states across extended sequences. Domain-specific physical rules are encoded during this phase. Stage 3 is post-training for real-time inference. The bidirectional attention from the original model is replaced with causal attention that enables streaming generation. Latent distillation reduces the number of inference steps from around 50 down to just 8 while maintaining quality. The result is a model that can generate frames at 16 FPS, fast enough for interactive use. Each stage builds on the previous one, gradually specializing the model while preserving what was learned before. This progressive approach is more stable than trying to train everything from scratch.
Now let's look at the core architecture, the diffusion transformer, or DiT blocks, that power LingBot-World. The model processes three types of input simultaneously: the current image or video context, action signals from user controls, and text prompts for semantic guidance. Inside each DiT block, information flows through four main layers. First is self-attention, which maintains spatio-temporal coherence by letting different parts of the video attend to each other across space and time. Second is the action injection layer. This is where user inputs get incorporated through scale and shift operations. The action signals are encoded as Plücker embeddings and injected via adaptive layer normalization, or ADA-LN. This modulates the features without disrupting what the model has already learned. Third is cross-attention, which integrates the semantic conditioning. This is how the semantic descriptions from the captioning pipeline influence the generation process. Finally, a feed-forward network performs the final feature transformation before passing to the next block. The model also uses a mixture of experts approach. High noise and low noise diffusion steps are handled by different expert modules, allowing the model to specialize, one for coarse global structure, another for fine details and textures. How does the model translate WASD keyboard inputs into meaningful camera transformations? The answer lies in Plücker coordinates, an elegant mathematical representation for 3D lines and camera rays. When you press W to move forward, that discrete input needs to become a continuous 6-degree of freedom camera transformation. The camera can translate in 3 dimensions and rotate around 3 axes. That's a lot of freedom that needs to be parameterized smoothly. Plücker coordinates represent each camera ray as a 6-dimensional vector consisting of a direction component and a moment component. The moment encodes both the position and orientation information needed to fully specify the ray in 3D space. This representation is particularly well suited for neural network processing because it's continuous and differentiable. There are no discontinuities or singularities that could cause training instabilities. Once the user input is converted to Plücker embeddings, it gets injected into the DiT blocks through ADALIN, adaptive layer normalization. The action embeddings scale and shift the normalized intermediate features, effectively modulating the diffusion process to respect the desired camera motion. This approach allows for smooth, controllable camera movements while keeping the injection lightweight. The model doesn't need to fundamentally change its architecture to support action conditioning. For real-time generation, the original bidirectional attention architecture has a fundamental problem. You need to see the entire sequence before you can generate any part of it. That's fine for batch processing, but impossible for streaming. LingBot-World solves this with block causal attention. Instead of every frame attending to every other frame, the attention is constrained to a lower triangular pattern. Each frame can only attend to itself and previous frames, never to future frames. This enables chunked processing. The video is generated in segments, with each chunk only depending on the chunks that came before it. As new chunks are generated, old ones are processed and cached, allowing for theoretically infinite generation length. Key value caching plays a crucial role here. When processing chunk n, we don't need to recompute attention over chunks 1 through n-1. Those results are cached and reused, dramatically reducing computation. The discriminator head uses cross-attention during training to provide adversarial feedback. It looks at the generated content and judges whether it's coherent with the conditioning, helping the generator produce more realistic outputs. The result is a model that maintains temporal coherence while generating frames fast enough for 16 FPS interactive use. This is what makes LingBot-World feel like a true simulator rather than just a fast video generator. Diffusion models typically require many inference steps, sometimes 50 or more, to generate high-quality outputs. For real-time use, we need to dramatically reduce this while maintaining quality. LingBot-World uses distribution matching distillation, or DMD, combined with adversarial training. The idea is simple. Train a fast student model to produce outputs that match the distribution of a slower, high-quality teacher model. The teacher model runs the full 50-step diffusion process. The student model tries to match those outputs in just 8 steps. A discriminator provides additional feedback, helping the student generate realistic details that might otherwise be lost in the compression. The training uses multiple loss objectives. Distribution matching ensures the student's outputs have the same statistical properties as the teacher's. Adversarial loss helps with perceptual quality. And a perceptual loss based on feature matching captures high-level semantic consistency. There's also a self-rollout component that's particularly important for world models. During training, the student generates multi-frame sequences and evaluates consistency across the whole rollout. This prevents the kind of drift and degradation that would otherwise accumulate over long generations. The end result is a 6x speed-up in inference while maintaining the quality that makes the world believable and consistent.
One of the most impressive capabilities of LingBot-World is what the researchers call emergent memory. The model remembers objects even when they've been out of view for extended periods. Consider the Stonehenge experiment. You start looking at the stone structure, then turn the camera away and explore other parts of the scene for over 60 seconds. When you turn back, Stonehenge is still there, exactly where you left it. This might sound obvious. Of course the rocks should still be there. But for most video generation models, objects that leave the frame essentially cease to exist. They might reappear with different shapes, different positions, or not at all. LingBot-World maintains a consistent world state throughout the generation. The model seems to have developed an internal representation of what exists in the scene, even for objects not currently visible. This is exactly the kind of object permanence that distinguishes a true simulator from a dreamer.
The practical implications are significant. You can generate coherent videos lasting 10 minutes or more. The world remains explorable and consistent, and characters or objects maintain their identities across complex interactions. This emergent memory wasn't explicitly programmed. It arose from the combination of the training data, architecture, and long-horizon training objectives. It's an encouraging sign that diffusion models can learn genuine world understanding, not just surface-level pattern matching.
LingBot-World enables several exciting applications that go beyond basic video generation. First is promptable world events. You can type natural language commands to modify the world in real time. Tell it to change to winter, and the scene gradually transforms with snow and cold lighting. Request fireworks, and they appear in the sky. The model responds with coherent environmental changes that make sense in context. Second is action agents. Since LingBot-World exposes a clean action interface, you can connect vision language models or planning systems to autonomously explore the generated worlds. The VLM observes the current scene, decides on an action, and the world model simulates the result. This creates a closed loop for training embodied AI agents without needing physical environments. Third is 3D reconstruction. Because the generated videos have consistent geometry, you can apply standard structure from motion techniques to extract 3D point clouds and meshes. This opens up applications in virtual production, game asset generation, and spatial understanding research. These applications span gaming, film and visual effects, robotics simulation, and creative tools. The combination of real-time performance, action controllability, and open-source availability makes LingBot-World a versatile platform for both research and practical applications.
Let's look at how LingBot-World performs on the vBench benchmark, a standardized evaluation for video generation models. On imaging quality, LingBot-World achieves 0.666, placing it at the top among compared models. Aesthetic quality comes in at 0.506, also best in class. And for dynamic degree, how much meaningful motion the generated videos contain, LingBot-World scores high while maintaining coherence. Compared to Oasis, another open-source world model, LingBot-World shows roughly 15% improvement in overall quality. Against GameGen, the visual fidelity gains are even more substantial at around 22%. But perhaps the most important comparison is with Genie 2, the world model from DeepMind. While Genie 2 may have comparable or even better performance in some areas, it remains closed and proprietary. LingBot-World makes all of its weights, code, and training recipes publicly available. The full codebase is on GitHub, model weights are hosted on Hugging Face, and there's a live demo where you can try the model yourself. For the research community, this level of openness is invaluable. You can study the architecture, reproduce the results, build on top of it, and adapt it for your own use cases. That's the kind of contribution that accelerates progress across the entire field. If you found this breakdown helpful, consider subscribing for more technical deep dives into the latest AI research, and definitely check out the links in the description to try LingBot-World for yourself.